In physics, work means a very specific thing. So work has the symbol W, and it is equal to the force times the displacement times cosine of the angle between them. So this is the definition of work. And really, if you want to write it in vector form, because we know that force and displacement are vectors, work is actually the dot product between force and displacement. That's where the cosine theta comes in. So if we have a block and a force F pulls on the block at an angle theta with respect to the displacement, and later on the block will be somewhere here with that force still acting on it, this would be the displacement of the block, and the work that this force does is its x component, so this is F cosine theta, times the displacement. So we want the force in the direction of motion of the block for determining the work that that force does. So work is something that's measured in joules, and the unit for joules is capital J. And unlike force and displacement, work is a scalar quantity. So it does not have direction, but it can be a positive or a negative. So no direction, but it can be positive or negative. So for instance, let's look back at the block, and let's say that there will be still this force F acting on it, but let's say that the surface is rough, so there will also be friction, kinetic friction in the opposite direction. The other two forces are the weight, and now it gets confusing because we have W for weight and W for work. The difference between them is that weight is a vector, so it has a vector symbol on top, and we'll use it in Newton's second law. And work is a scalar quantity, so there won't be the vector symbol on top. And then there's also the normal force. So let's say that these are the forces that act on the block. We can solve for the work due to each individual force. So work done by force F as this block is moving a distance d is going to be force F times the displacement times cosine of the angle between the force and the displacement. The work done by the normal force will be the normal force times the displacement times the cosine between the displacement d and the normal force Fn. That angle is 90 degrees. Cosine 90 is 0. So that means that the work done by the normal force is 0. Normal force pulls up on the object. In no scenario will that block move to the right if the normal force pulls up on it. The work done by the weight is going to be weight times displacement times the angle between displacement and weight, which is again 90 degrees, so we have cosine 90 degrees. And then we have the work done by the friction force, and that is friction force times displacement times the angle between displacement and the friction force, and that is 180 degrees. So we have cosine 180. Cosine 180 is -1, so work done by the friction force is negative FKD. Okay, so if I want to write the net work in this particular problem, so I'll say work net. Since it's a scalar, I can just add all of these components up. So I have work done by force F plus work done by the normal force plus work done by the weight plus work done by kinetic friction. So that will be Fd cosine theta plus 0 minus Fk times d. So the net work is just Fd cos theta minus the friction force times d. Now, if we have a force that is not constant, so in this example above, the force was constant, but let's say that on the y-axis we have F cosine theta, and on the x-axis we'll have just the displacement d, and the force has some strange shape, it's not a constant force, then to find the work, what we would have to figure out is the area under the curve. So the area under the curve here is work. So work is area under the curve. The curve, of course, will have to be, the graph will have to be of force versus displacement. But there is another special case where work is area under the curve, and that is what we call a PV diagram. So we use that in thermodynamics. On the y-axis we have pressure, and on the x-axis we have volume. So if our process is an isobaric process where the volume stays, the pressure stays constant, there we go, but the volume is changing, then the area under this curve is also work. So in this case, work is P delta V, because we're just dealing with rectangles, and the area of the rectangle is width times height. So these are some examples of work. In the next video, we're going to look at how work is related to forms of energy.